Let us now discuss the SimpleRISC ISA. So SimpleRISC is an assembly language that we shall create. You and me shall create from scratch. So this is supposed to be a very simple RISC-like language that has a very few that has few instructions, and the instructions have a very regular structure. So as we go through the next few slides, we'll see what it takes to actually build and design an assembly language, and we shall look at the nitty-gritties of designing one such language. So let's take a look at SimpleRISC. So SimpleRISC is a very simple, as the name suggests, it is a very simple assembly language, one of the easiest to learn. So my thinking is that it's better to learn a very simple assembly language and get an idea first before moving on to real world assembly languages such as ARM and x86, because they have a lot of other details which might overwhelm the reader at this point of time. So we'll design an assembly language called SimpleRISC, and then we'll design a simple binary encoding for it, which means to convert instructions into a sequence of zeros and ones. And then in the processor chapter, we'll create a processor to actually implement the SimpleRISC instruction set. So let's have a brief survey of instruction sets. So almost every processor vendor has created its own instruction set. So let's go way back to 1977 when the VAX instruction set was created. It was a very complex RISC instruction set with a lot of instructions. It had 16 registers, and it used a little endian format. Then one of the more popular instruction sets was the Sun SPARC instruction set. So there were actually two variants of SPARC. The 32-bit variant was introduced in 1986, and the 64-bit variant was introduced in 1993. So what 32 bits means that one instruction was 32 bits. In SPARC, the size of a register was 32 bits. So that's what it means to be a 32-bit instruction set. And what it means to be a 64-bit instruction set is also the same. The size of a register is 64 bits, or the size of an instruction in the case of a RISC architecture is 64 bits. So the 64-bit instruction set was actually bi-endian, means it could be configured to be either little endian or big endian, and we have 32 registers. Then we come to the PowerPC instruction set, which was mostly used by IBM, and later Apple and Motorola used it. So PowerPC showed a similar evolution. They had a 32-bit instruction set in 1992, and then migrated to a 64-bit instruction set later on, and both of them were bi-endian with 32 registers. Similarly, HP had its own instruction set, PA-RISC, that's still used in high-end HP servers, and Motorola had its M68K or M68000 instruction set. That is still that was being used in Motorola processors. So now, of course, they are not in the processor business anymore. Another very popular instruction set is the MIPS instruction set, which is also a RISC instruction set. MIPS has 32 registers. So now MIPS is used in some small embedded processors, but most of the embedded processors have actually migrated to Intel and ARM. Here is one more instruction set which is my personal favorite. The reason being that this is the first instruction set that I had learned, is the DEC Alpha instruction set, introduced circa 1992. So it started out as a 64-bit instruction set with 32 registers. Then we come to the x86 instruction set, which is actually a family of instruction sets. It's not just one instruction set, but many. So Intel started its journey in 1978 with a 16-bit instruction set, that had 8 registers. So this x86 instruction set is now an open standard. So it is used by AMD. It's actually used by many other vendors as well. Because so even since the standard is open, readers can implement their own processors with the x86 instruction set. So around 1985, Intel transitioned to a 32-bit instruction set, again with 8 registers. And then as recently as 2003, both Intel and AMD together migrated to an x86 64 instruction set. Actually, AMD was the first to migrate, and Intel then migrated. So AMD came up with the Opteron processor that had a 64-bit instruction set called x86 64. So all Intel instruction sets have been little endian, and the 64-bit instruction set of Intel, which we shall also take a look at in the 5th chapter of this book, has 16 registers. Lastly, the latest entrant in the world of processors and instruction sets is ARM. So ARM is a very interesting company in the sense that ARM does not make its own chips. Rather, ARM makes the design of a processor and sells the design to other companies like Texas Instruments or Qualcomm or Samsung, and then they make a chip and embed some additional elements if required, and then they make and fabricate a chip out of it. So ARM is not that new. In fact, ARM used to exist way back in 1985 when they came up with a 32-bit instruction set. But of late, ARM processors are gaining in prominence, and a big reason for that is that ARM processors are used in mobile phones, and mobile phones have spread exponentially. So in 2011, ARM also came up with a 64-bit instruction set for larger computing devices such as tablets and possibly servers. And so the 64-bit instruction sets are always targeted for larger devices. So we'll see why. So we'll have a lot of opportunities to discuss what's the advantage of a 64-bit instruction set, but this is not the right point for it. So ARM is also bi-endian. Little endian is the default, but it can be configured to be big endian. So big endian or little endian is just a matter of convention. Let us now discuss the basics of the SimpleRISC instruction set. So let SimpleRISC have 16 registers, and as is the convention, let us number the registers from R0 till R15. So the 14th and the 15th register, R14 and R15, let me refer to them with special names. So let us refer to R14 as the stack pointer or SP. Similarly, let us refer to R15 as the return address register or RA. So the meaning of the term stack pointer and the return address register will be they actually correspond to pretty complex concepts. So we'll discuss what they are in the future slides, but let's just remember for the time being that the stack pointer SP is R14 and R15 is will also be referred to as the return address register. So they have some special meanings. So coming to the view of memory, let's assume a von Neumann model where we assume that the memory is one large array of bytes. It contains data as well as the program, and a program assumes that the entire memory is for its own personal consumption and there are no other programs. So let's live with some very simplistic assumptions for the time being. So let's also have a special flags register which contains the result of the last comparison. So let me give an example. So this register is not visible to the assembly programmer. However, it will be visible to the hardware designer, and that's very important. So let me show an example here. So the example is let's have a compare in SimpleRISC assembly where we compare the contents of register R1 and R2. If the contents are equal, what the hardware would do is that it would set the E bit inside the flags register. So if let's say, as R1 is equal to, let me put a C style equal to. If this is the case, then you set, the hardware sets flags.E equal to 1. If R1 is greater than R2, well then flags.E, so the default value of E and GT is 0, so I am not mentioning that, so the E field in this case is clearly 0. So we set flags.GT greater than as 1. If R1 is less than R2, so clearly the equality flags.E is 0 and flags.GT is 0. So we can thus make out what is the result of the last comparison by taking a look at these two flags, flags.E and flags.GT. So this is the broad idea, but we'll get a chance to discuss the meaning of these two flags in great detail when we look at the compare instruction. Now it's time to take a look at our first assembly instruction. So let's introduce our first basic assembly instruction. It's called the move instruction. The job of the move instruction is very simple. So it comes in two flavors. So in one flavor we transfer the contents of a register into one more register, and in the second flavor we transfer an immediate, a constant to a register. Right, so these are the only two variants of the move instruction that are possible, and the way that we actually write an assembly statement is like this, that we first so in SimpleRISC what we do is that we first write the name of the assembly opcode, which in this case is move. Then we write the destination, and then we give a comma, and then we write the name of the source. So for example, if we write move R1, 3, which essentially means set R1 equal to 3. That's what it means. Right? Let me also put the comment sign to indicate that this is not a valid assembly statement. So what we are doing here is that we are taking the value 3 and setting it to register R1. So you can think of this as similar to any statement in C or Java where we write something of the form x equals 3. So in this case x is the variable, and we are setting the value of the variable to 3 or 4 or 5 or any immediate value. Also we can have a statement x equals y. So in this case this is same as move R1 R2, where the contents of R2 are moved to R1. So the value of the immediate in this case is actually embedded inside the instruction. So SimpleRISC supports 16-bit immediates, and the range of an immediate is, so this is a 2's complement number, and the range of an immediate is from minus 2 raised to the power 15 to 2 to the power 15 minus 1. So this is the standard 2's complement range for a 16-bit number. So now let's look at another family of instructions. Since the entire family is very similar, I have listed all 6 together in the same place. So SimpleRISC has 6 arithmetic instructions, and as the name suggests, they are addition. Let me just change the pointer. Addition, subtraction, add, sub, mul for multiplication, div for division, mod for getting the remainder, right? So this is basically getting the modulo or the remainder, and CMP is for compare. So the compare instruction is slightly special, but the rest are very straightforward. So let's take a look at the add instruction first. So the add instruction is actually a 3-address format instruction. What this essentially means is that it takes 3 arguments. So the destination always has to be a register. The second argument has to be a register. And so basically, if you want me to write this slightly formally, so the destination which comes first has to be a register. The second operand, which is actually the first source operand, has to be a register. The third operand can either be a register or an immediate. So that is a constraint on the third operand, which can either be a register or an immediate. So here, as if we write add R1, R2, R3, essentially what we are instructing the machine to do is take the contents of R2, take the contents of R3, add them, and save the result in R1. Similarly, if I say R2 and 10, I can say R2 plus 10. So this is the simple add instruction, which has a nice analog with traditional programming languages, where if you write, a C function of the form x equals y plus z, we can directly translate it to an assembly instruction of this form. Fine. So after the addition instruction, the rest 4 instructions, sub, mul, div, and mod, have exactly the same format. So I have not shown the immediate values over here, but I'll explain with examples. So these 4 instructions over here, as the name suggests, the subtract instruction subtracts the contents of R3 from R2. So it sets R1 equal to R2 minus R3. So in this case, it is possible to write the subtract instruction with the third operand being an immediate as well. But mind you, only the third operand can be an immediate, not the other ones. So I can write very well R1, R2, and 10. So what this will essentially do is that it will set R1 to R2, the contents of R2 minus 10. So I have not shown this case for lack of space, but the third operand can either be a register or it can be an immediate. Any register or it can be an immediate. Same is the case for multiplication, exactly the same format. So let me write a multiplication instruction with the third operand as an immediate. So we shall see that the way of specifying the format is the same. So I can very well write mul R1, R2, and 10. So this would set R1 equal to R2 multiplied with 10. So division and mod have also the same format, where we divide R2 by R3 to get the quotient, and we take R2 mod R3 to get the remainder. So these are the 5 add, sub, mul, div, and mod are the 5 arithmetic operating instructions, and as we can see, they are very similar to their high-level programming equivalents. So it is just that they are written slightly differently. So one thing that is common is that even in a high-level language, such as this statement over here, the destination comes first. Subsequently, the arguments come later. This is the same case in assembly as well, where the destination comes first and the operands or arguments come later. So this is one similarity. The other similarities are that we also, we clearly mention what is the operation that we want to perform. So either it's an add or a subtract, a multiplication, division, whatever is the operation that is, that is placed at a different point. So plus is over here, but in assembly we first mention what is the operation. But other than this small difference, this statement like add R1, R2, R10 is pretty similar to what we would actually write in a high-level programming language. Assuming R1 and R2 are variables, we would write R1 equals R2 plus 10. So now let's take a look at the compare instruction, which is actually very interesting because it is different. So we typically don't write compare instructions of this type in a high level language. So in this case, what we do is that we pretty much subtract R1 minus R2. If the result is equal to 0, then we can infer an equality. So we set flags.e, which is the equality flag, to 1. If R1 minus R2 is greater than 0, then we can set flags.gt equal to 1, which basically means that R1 is greater than R2. It indicates the fact that the greater than flag is 1. Similarly, if R1 minus R2 is less than 0, then both the equality flag and the greater than flag both will be set to 0. So we can infer a less than condition. So it is important to note that in SimpleRISC, the only instruction that sets the flags is the compare instruction, and the flags remain in their state till the next compare instruction. So let me explain with an example. Assume you have a compare instruction. So the compare instruction will essentially go and set the flags. After that, we can have many other instructions, but till the next compare instructions, the flags maintain their value and they can be used by other instructions, as we shall see later. Now let's take a look at a very simple program and let's try to convert it into assembly language. So let's outline a generic method. So assume that we have this code snippet here in a high level language. The question is, how do we convert it to an assembly language? So the first thing that we do is that we assign the variables here to registers. That's the first thing. That's always what we do. That's the first thing, that we assign the variables to registers. So let us assume that variable A is assigned to R0, B to R1, C to R2, and D to R3. Right? So this is the assignment of variables to registers. So now what we do is that A equals 3 just becomes move 3 to R0. B equals 5 becomes move 5 to R1. C equals A plus B. This essentially means add R0 and R1. And let's assign it to R2, because R2 and C are, R2 and C are, R2 is supposed to contain the value of C. Then to subtract C minus 5, we again take R2, subtract 5 from it, and save the result in R3, which is essentially mapped to D. So here we have 4 high level statements and 4 assembly statements because it's a simple program. But in general, the number of assembly statements will typically be more, sometimes much more. But the important thing to note that it is fairly simple to map a high level program to assembly. What essentially needs to be done is that so there are 2 steps. First is assign the variables to registers. That is step 1. Step 2 is that after the assignment, each and every high level statement gets converted to assembly. So the important point that all of you need to note, that writing assembly programs is pretty much similar to writing high level programs. And irrespective of how many books you read or how many online courses you take, such as this one, the only way that a student will actually get the ability to write high quality assembly code is to physically go and write as many assembly programs as possible. Practice makes perfect. So only by writing more and more assembly programs would a student actually get some expertise of how to write assembly programs and would get the confidence of writing assembly programs. So the course and books and other material is fine to at least introduce the concepts, but the real knowledge will be gained only by writing and by practice. So if you go to the website of this book, you will find SimpleRISC emulators which allow you to write assembly programs, and subsequently the emulator will run the assembly program instruction by instruction and finally print the result. So let's now take a look at one more example. A equals 3, B equals 5, multiply A and B and compute C mod 5. So again the first stage is assign the variables to registers. So A, R0 is mapped to A, R1 is mapped to B, R2 to C and R3 to D. So the first two statements are the same as what they were in the previous example. Then we multiply R0 and R1 and we save the result in R2. So R2 is C and then again we do R2 mod 5. So I'm putting the percentage because that's what it is in C. And we do R2 mod 5 and save the result in R3. Now let's take a look at the compare instruction. The compare instruction is different. It's a different concept. It's not there in high level languages. So let's say we want to compare 3 and 5 and then the idea compare 3 and 5 and then we want to print the value of the flags not in assembly but at least as a part of the answer. So it should actually be write the value of the flags. So assume A is 3 and B is 5. So we first do a register assignment. We move 3 to R0, 5 to R1 and we compare R0 and R1. Since 3 is less than 5, we'll have the less than condition, right? So what we have is that 3 is less than 5. So there is no equality and there is no greater than. So the equal flag will be 0 and the greater than flag will be 0. Now let's compare 5 and 3. So in this case they get reversed. So we can clearly see that 5 is greater than 3. So in this case the flag for equality is 0. But the flag for greater than flags.gt is equal to 1. So this essentially means that the comparison yielded a result and the result was that the first operand is greater than the second operand. So that's the reason the gt flag flags.gt is equal to 1. Lastly, let's compare two numbers with the same value 5 and 5. A is 5 and B is 5 and let's compare A and B. So we move 5 to R0, we move 5 to R1, we compare R0 and R1. So flags.e in this case is equal to 1 and flags.gt is equal to 0. The flags.e is equal to 1 because there is an equality. We clearly see that 5, so I'm writing the equal to the same way that is written in C, equal to. So we clearly see that 5 is equal to 5. So there is equality, there is no greater than. So the greater than flag is 0, but the equality flag is 1. Now let's show some more examples. So let's say write assembly code in SimpleRISC to compute 31 divided by 29 minus 50 and save the result in R4. No problem. So mind you, this is integer division. So 31 divided by 29, the answer will be 1. So let's map them. Let's map 31 to R1. Let's put 29 in R2 as can be seen in these two statements. Then let's divide R1 divided by R2 and the result will get saved in R3. And from R3 we subtract 50, so we compute R3 minus 50 is equal to R4. And R4 contains the final result as mentioned in the question. So this is how we write assembly programs, but these are very simple examples of assembly programs. So my advice to the student or the reader would be to actually go and write as many assembly programs as possible. And I would say that by the end of this course, the student should have written at least 3000 lines of assembly programs, 1000 each in SimpleRISC, ARM and x86. That would at least give the student a basic understanding of how assembly programs are to be written. Now let's move ahead in our journey of introducing instructions and introduce 3 more. So these are logical instructions which compute a bitwise AND or an OR or a NOT. So let's look at some of these. So the AND and OR operations are exactly in the same vein in the 3-address format as the add, subtract, multiply operations. So in this case, the first two operands have to be registers, and the third operand has to be either a register or an immediate. So the AND operand computes R1 is equal to R2 and R3, where this is the bitwise AND. So let me give an example of a bitwise AND just in case people have forgotten. So let's say 1 1 0 0, bitwise ANDed with 0 1 0 1. So 1 and 0 is 0, 0 and 0 is 0, 1 and 1 is 1, 0 and 1 is 0. Similarly, we have bitwise OR, which can do R2 or R3, and so we have a bitwise OR over here, which is exactly the same, but we replace the AND sign by an OR sign. Then we have the NOT operand, which is actually a 2-address format operand. So we have only one source. We only have one source operand, which can be either a register or an immediate. So in this case, what we do is that So in this case, so if there is a single source operand, so what we can see as a general rule, that only one source operand is allowed to be an immediate, but both the source operands are not allowed to be immediates. So when we say not R1, R2, what this essentially means is that let's say the value of R2 is 0 0 1 0. We take a NOT of it. Once we take a NOT of it, this becomes 1 1 0 1. So the second argument in this case can either be a register or an immediate, the second source argument. So now let's compute A or B. So now let's consider an example. So in this example, we compute A or B. So assume that A is stored in R0 and B is stored in R1. Let's store the result in R2. So it's very simple. We do it the same way as our add, subtract, multiply instructions. We compute OR R2, which is essentially equal to R0 or R1. So this is similar to R0 or R1. So let's move ahead and introduce some more instructions that are required. So let's discuss the shift operations. So shift operations are something like this, that let's first discuss the left shift operation. So consider the number 0010. So if we left shift it by 2, which means that every bit moves 2 positions to the left. So in this case, if 0010 is being left shifted by 2 positions, so what will we have? What we'll essentially have is that the 1 will come over here, 0 will come over here, and the 2 new positions will be created. In this case, we just add 2 more zeros. So 0010 left shifted by 2 is equal to 100. So we can clearly see that this number is equal to 2 and this number is equal to 8 in decimal. So left shifting by n positions basically means that it is the same as multiplying a number by 2 to the power n. So why is this the case? So we shall see in some time. So let me just give one more example of left shifting. Let's assume that the number is 1010 and we left shifted by let's say 1 position, right? So we left shift the number by, shift it to the left by 1 position. So in this case, 0 will come over here, 1 will come over here, and a new position will be created. We put a 0 over here, assuming the number is remaining within 4 bits. So the reason that this is equivalent to multiplying it by 2 to the power n is can be found out. There are many arguments, so maybe let's start with a couple of examples. So let's take a look at this example. This number is 2 in decimal and this number is 8 in decimal. So what we are essentially doing is that we have left shifted it by 2 positions, which is equivalent to multiplying this number by 2 square. So the multiplication argument is actually interesting, and the reason that this holds is that any number in a binary expansion can be thought of as, well, so let's start counting from 1, because in general we have done that in other places as well. So assume I goes from 1 to n, any binary number can be expressed in this form. Now if we, let's say, left shift the number by k positions, so what this number essentially becomes, right, that's the most important thing, is that this number essentially becomes right. So basically the number remains the same and it is left shifted by k positions. What it essentially becomes is that it is pretty much the same number, but each of these coefficients, the coefficients remain exactly the same, the set of coefficients, right, because it's getting shifted to the left. But these exponents over here pretty much get multiplied, get offset by a factor. So actually what I can do over here is that I can replace this again as it was. So for those who have followed the math over here, what we have done is that we have taken a number and we have left shifted it by k positions, but we have not gotten rid of any digits. So that is important, that we have not gotten rid of any digits per se. Then what we have done is, this is exactly the same as, instead of so the first k positions have zeros, so we don't count them. Then from k plus 1 till n plus k, from k plus 1 till k plus n pretty much, we had the same set of coefficients which we had earlier, and but the thing is that the powers of 2 pretty much get shifted or get multiplied by 2 to the power k. So what we do is that we sort of do a little bit of algebra, and so we separate the 2 to the power k from the equations, and so what we are left with is that this becomes the original number n multiplied by 2 to the power k. So what we see is that this is a nice way, unless there are overflows, right, we are exceeding the range of the number system, then it's a separate issue. But if that's not happening, this is a nice way of actually multiplying a number by any power of 2, right, multiplying a number by 2 to the power k. So let me maybe consider, let's say, one more example. Consider 0, 0, 1, 1. We then left shifted by 1 position. So this becomes 0, 1, 1, 0. In decimal, this number is 3 and this number is 6. So this is equivalent to multiplying 3 with, multiplying 3 with 2 to the power 1. So we get 6. Alright. So given that left shifting actually works, let us see if left shifting holds for negative 2's complement numbers. Here again we assume that there are no overflows. Instead of cluttering up this PowerPoint slide, let me actually move to another software. So now let's see that whether left shifting actually holds for negative numbers. So in this case, let's consider a negative number -2 in a 4-bit system. So -2 is 1110. Fine, so let us take this number and let us left shift it by 1 position. So then this becomes 1100. So 1100, what is it? It is -4. So we see that it holds. Let's consider one more example, -3. So -3's representation in the 2's complement notation is actually +13. So which is 1101. No problem. Now let's left shift it by 1 position. So then what do we get? 1010. So what is this? So this is 8 plus 2 is 10. So in decimal, this is 10 minus 16 or -6. So what we see is that left shifting holds for even positive numbers as well as negative 2's complement numbers. So now that we have discussed left shifting, let us discuss what is right shifting. So let's go back to the slides and discuss what is right shifting. So in right shifting, what we do is there are two kinds of right shifting. There is arithmetic right shifting and logical right shifting. So in arithmetic right shifting, which is represented by another operator, if we right shift this number by 1 position, what we do is that all the bits move 1 position to the right, but the important point is the sign bit. So the sign bit in this case is replicated. So if the sign bit was originally 0, we just replicate the sign bit and have one more 0. And if the sign bit was originally 1, we just replicate the sign bit and have a 1. So what my claim is that right shifting is similar to dividing a signed number by 2 to the power n, and the proof will exactly be the same as the way we proved for a left shift, and it's just that instead of 2 to the power plus k, it will become 2 to the power minus k. But let's consider examples. That will be a lot of fun. So let's again consider a 4-bit system, and let's consider 0 1 0 0. So this is equal to 4. Now let's right shift it by 2 positions. We'll get 0 0 0 1. So this number was 4 and this number is 1. So we see that division holds. Now let's consider negative numbers. So let's see, consider -6, which is 1 0 1 0. So let's right shift it by 1 position. In this case, if we right shift it by 1 position, this is how all the bits will actually move. So no problem. Let's write 1 0 1 and we replicate the sign bit. So this number is 8 plus 4 12 plus 1 13. So in 2's complement, this is 13 minus 16, or this number is -3. So we clearly see that right shifting a number by n positions can be a positive number or can be a 2's complement negative number is same as dividing a signed number by 2 to the power n. So a logical left shift and an arithmetic right shift essentially are very useful operations, and they help us in multiplying or dividing numbers by 2 raised to power n, by any power of 2. Alright, so now let's consider a logical shift right, which is actually represented by the 3 greater than operators, right? The terminology has come from Java. So in this case, the sign bit is always set to 0. So this is the same as dividing the unsigned representation by 2 to the power n, right? That is its connotation. So in this case, we just move all bits 2 steps, n steps to the right, and the MSBs are filled with zeros. So the food for thought question over here is that why don't we have an arithmetic shift left? Well, the reason is that the sign bit always gets overwritten by numbers from the left. So there is no meaning of an arithmetic shift left. You only have one shift left, but two shift rights. So we have a couple of SimpleRISC instructions, which will, 3 to be precise, and their format is exactly the same as the add, sub, multiply instructions. So the logical shift left instruction, the destination comes first, which is a register. The first source operand is a register, and the second source operand can either be a register or an immediate, reg/im, right? Either a register or an immediate, and the name of the instruction is LSL, logical shift left. Similarly, we have a logical shift right operator, which is called LSR, exactly same notation. And we have an ASR, an arithmetic shift right operator, which is called ASR. So what are the three new instructions that we are introducing? The three new instructions are LSL, LSR, and ASR. Logical shift left, logical shift right, and arithmetic shift right. So let's give some neat examples with shift based instructions. Let's assume we want to compute 101 multiplied with 6 with just shift based operators. So the first task is register assignment. So we move 101 to register R0. So we shift R0 by one position, which is essentially equal to R1 is equal to 101 multiplied with 2, because we are shifting it by one position. And in this case, then again we compute R2, which is shifting 101 by two positions and multiplying it by 4. Then we add R1 plus R2 and set the result equal to R3. So essentially R3 becomes 101 multiplied by 6. So, a skeptic would ask that why did we do this? We should have simply loaded 101 into R0 and written an instruction of this form. As simple as this. We should have taken R0, multiplied it with 6 and saved the result in R0 or R3 or any other register, right? Why did we have to have two shifts? Here is the answer. So typically in hardware, multiplication and division, right? Multiplication and division are very expensive operations. Expensive in the sense that they take a lot of time, right? So I can say, plus in terms of time, right? They take a lot of time. So a lot of compilers actually, a lot of compilers and good programmers encourage the user not to use very expensive multiplication division instructions and use shifts instead, which are very fast, right? So shift instructions are ultra fast. So the shift instructions are ultra fast and they are extremely fast. So that's the reason it is a good idea to use shift instructions in the place of expensive multiplication and division instructions wherever it is possible. So let's consider one more example, which is not that difficult once you know the answer. So let's compute 102 times 7.5 with the help of shift operators. So what we can do, the first thing is assign 102 to a register R0. So then we shift it to the left by 3 positions, which means R1 is equal to 102 multiplied by 2 to the power 3, which is 8. And then we shift it to the right, right? So since 102 is positive, logical and arithmetic shift right are the same. So we shift it to the right by one position, which means multiply 102 with 0.5. Well, then it is very straightforward. We subtract R1 minus R2. So R3 becomes equal to well, this is exactly what we wanted to do. So you see, this is very easy. And instead of, we have avoided the costly, expensive, time consuming division instruction, and in the place of that, what we have done is that we have a very, very nimble and efficient solution with shift instructions. Okay, now let's introduce some of the real instructions that help us write big and scalable programs. So let's introduce load store instruction. So a load store instructions job, so essentially a load instructions job is to take a value from memory and bring it into a register. So this is a load instruction. And a store instructions job is to take a value from a register and put it in memory, right? So what does a load instruction do? It takes a piece of data from memory and puts it in a register. And similarly, a store instruction takes data from a register and puts it in memory. So let's take a look at the format of a load instruction. So in a load instruction, the register which needs to be loaded or is the destination, right? So this is the destination, right? In this two address format, the first is the destination and the other uses base index. I'm sorry, not base index, it is base offset addressing. Yeah, it should be base offset. Addressing. So in this case, what we do is that the base address is specified in register R2. So we take register R2, we add 10 to it, we get a new memory address. We access the memory using this address, read the contents and put it in R1. So in this two address format instruction, the second operand is always points to a certain memory location, a value in a memory location. The hardware's job is to read this value that is there in the memory location, to read this value and put it in a register. So store instruction has exactly the same format, right? But the store instruction, if you think about it, does not actually have a destination. The destination is memory. It does not have a register destination. So what the store instruction does is that the register that needs to be read, right? The register that is actually read is specified first, and then the memory location is specified after this, using exactly the same addressing mode, a base offset addressing mode. So let's show this thing graphically. So graphically what we do is that in the case of load, we take the value of R2. One second. We take the value of R2 from the register file, we add 10, we get the address. This address is used to access memory. In a 32-bit system, we read 4 bytes from memory, which is the data. The data comes back and it is fed into the register R1. So instead of 4 bytes, it can be, in a 64-bit system, it can be 8 bytes. That doesn't matter. So in this case, in a 32-bit system, we read 4 bytes from memory and put it in a register. So store actually does the reverse. So in this case also we compute the address, but instead of the flow of data being from memory to a register, the flow of data is actually reverse. It is from a register to memory. So let's give an example of a load store based. So let's consider an example with arrays. So let's assume that an array's base address is stored in R0. So the way that an array would actually look like in memory is something like this, that an array with 10 integers, where one integer is 4 bytes, is a contiguous region of 40 bytes. So in this case, let's assume that the base address of the array is R0, which means the first integer is stored in the locations that R0. So let's assume that the contents of R0 are V. So the first integer is stored in the locations V to V plus 3. The second integer is stored in the location V plus 4 to V plus 7, and so on. So we can say that maybe the starting address of the array, in this case array 0's starting address, is actually V. The starting address of the first entry is V plus 4, and so on. So similarly, the starting address of the ninth entry, the ninth and the last entry in the array where we start counting from 0, is essentially V plus 36. So given this simple argument, which I'm sure most of you would have learned in your basic C or C++ or Java programming class, let's try to implement this small program in assembly language. So we have an array of 10 integers where we assume the base of the array is saved in register R0. We set the third element to 5, array 3, right, the element at index 3 to 5, the element at index 4 to 8, and we set R5 is equal to R4 plus R3. So, alright, so now let's do some amount of register assignment. So let's move the constant 5 to R1, and let's save the value R1 in actually the location array 3. So what is the starting address of array 3? Well, the starting address of array 3 is pretty much R0 plus 12. The reason being, let's go back to this discussion over here. So the starting address of array 0 is the contents of R0. Starting address of R1 is contents of R0 plus 4. Similarly, the starting address of array n is R0 plus 4 times n minus 1. Sorry, R0 plus 4 times n. So in this case is R0 plus 12. So we write it as 12 R0. So this is a very, very important point to understand, and I want to ensure that all of you have more or less understood it. So the idea is that what is the contents of R0? R0 pretty much points to a memory address in memory that contains 40 contiguous bytes. So the first 4 bytes are R0. The next 4 bytes are R1, and so on. So what is the starting address of R0? It is of array 0. So starting address of array 0 is R0, right? Let's say the starting address. Yeah, the starting address of array 1, R1, is R0 plus 4. 4 bytes, because the size of one integer is 4 bytes. Similarly, the starting address of Rn is R0 plus 4n. So that's the reason the starting address of R3 is 12 R0. So we save the value. So we do the same. So we do what we have done here. We do the same for R4, where we save 8 in R2, and then we store the value of R2 in 16 R0, which is essentially the same as setting R4, array 4, is equal to 8. Finally, we add R1 plus R2 because they contain the values that were stored, and we save it in R3, and the value of R3 is again saved in 20. 20 is the offset and R0 is the base. So this is essentially equal to the fifth memory address of the fifth element. So here we save R3, which is R1 plus R2, or in a sense the same as so by this time the advantage of using a base offset addressing mode should be clear, that it allows us to implement arrays. So what we can do is that we can save the base address in an array, and then we can use the offset to actually access different elements of the array, right? So we always need to be mindful of the size of an element. So in this case the element is an integer and the size of each element is 4 bytes. That's the reason to go to the nth element, where we start counting from 0, is the starting address plus 4n. So once that is clear, we can write programs of this type to load and store values from memory, from different data structures in memory, the array being 1, to read them into registers, work on them and write them back. Now it's time to actually get to the real fun part of assembly instructions. And so what have we covered up till now? We have covered arithmetic logical instructions, and we have covered load store instructions, right? So it is now the apt time to actually get into the real fun part of assembly programming, which is to add branching. When we add branching, we'll be able to implement high level concepts such as if statements, for loops, while loops and so on. So as I had mentioned in some of the early slides, that an assembly statement can be associated with a label, and this label can be used to uniquely indicate a assembly statement. What we can later on do is that we can have this statement b.foo, where the branch statement would essentially transfer the control of the program from this particular line over here to this line here. So the program counter would initially be pointing to this line, and subsequently it will start pointing to this line, and this statement will get executed. So the branch statement in assembly is very simple. We just do b and then the name of the label. So the format in this case is b and the name of the label. So there are some conditional branch instructions as well, where we'll actually see the power of having the flags register, right? So let's have a BQ instruction, branch if equal. So what this means is that, look, we first have a compare instruction. We have many more instructions that are not compares, and then we have a BQ instruction. So this instruction first takes a look at flags.e. If flags.e is equal to 1, means that this compare over here had resulted in an equality, it will jump to foo, pretty much branch to foo. The same is true with the BGT instruction, which takes a look at flags.gt, and if flags.gt had been set to 1 by the last compare instruction, the BGT instruction would jump or branch to .foo, essentially the statement which is there at the .foo label. And these flags, mind you, are only set by compare instructions. And who are they meant for? They are meant for later branch instructions like BEQ and BGT to take a look at them and jump. Alright, so now it is time to write slightly difficult programs and realize the power of assembly language. So let's try to write this program. If R1 is greater than R2, then let's say 4 in R3, else we say 5 in R3. So well, that's easy. The first thing that we do is that we compare R1 and R2. So if R1 is greater than R2, then so we always come one statement down. If it's greater than R2, the flags.gt bit would be set to 1. So if it is greater than, we jump to GT label, which is over here, and we save 4 in R3. Otherwise, we don't jump, and by default we come to the next statement where we save 5 in R3. So this is a simple program which shows us the power of the BGT instruction, that if the relevant condition is true in the flags register, then we jump to the target. In this case, the target is .gt label. Otherwise, we just go to the next or the subsequent instruction. Now let's move on to a more complicated example, and this is a genuine assembly program in the sense it has most of its features. So let's compute the factorial of a variable called num, right? So which is as specified in the C program over here. So to write a program in assembly language, let us maybe add a step 0. If the program is complicated, it might actually make a lot of sense to first write it in a high level language such as C or Java. The reason for that is that it will help us visualize all the parts, and it will become fairly easy for us to actually code it. So we'll follow this approach over here. So to compute a factorial, first we define the product variable, which is initialized to 1. Then we define an index that starts at num, and we assume, for all practical purposes, num is a large enough number, so we don't have to check for special cases. So here, if idx is equal to, we start the index, a for loop, equal to num, and we keep going till num reaches 1, and the moment reaches 1, we jump out of the loop, and we subtract the index. We keep going till idx reaches 1, and we subtract the index by 1 in each step, and this is the multiplicative step, prod equals prod multiplied by idx. So this code is enough to compute the factorial of a number. So recall that the factorial of a number n factorial is 1 multiplied by 2 all the way till n, right? So let us now try to convert this program to SimpleRISC. So in this case, the first thing that we do, step 1, is register assignment. So R1 is assigned to prod, and so we set prod equal to 1, and we set, so this is idx, so R2 is assigned to idx, and we initialize it with num. So as the assumption here is that num is assigned to R0, so R0 contains num. So that is the assumption. That's the assumption that we begin with. So sometimes if the assumption is not specified in the question, users can make their assumption, as we have done over here, that the num variable whose factorial needs to be computed is there in R0. And so what we do is that the variable idx in the C program, we assign it to R2, and we set R2 equal to R0, where R0 contains num. So essentially the starting value of idx is equal to num. Subsequently, we add the dot loop label over here to signify the fact that later on we might want to jump to this point. Then what we do is that we multiply R1 with R2. Recall that R1 is mapped to prod, R2 is mapped to idx. So we set R1 equal to R1 times R2, which is equivalent to prod equals, the product is equal to product times idx. So this is the multiplicative step. Then what we do is that we subtract the index, we subtract 1 from the index, which is essentially this step over here. We subtract 1 from the index. So idx equals idx minus 1. So when do we actually stop the loop? We stop the loop when the index becomes equal to 1, because there is no point multiplying a number by 1. So we compare R2 with 1. Alright, so we compare R2 with 1 in this step, and we see if R2 contains IDX, if IDX is greater than 1 or not. If IDX is greater than 1, then the flags.gt bit would have been saved. So in this case, the BGT condition would evaluate to true and we would jump to loop, which is essentially we will jump back like this. So what we have done, we have actually these 6 lines. I would advise the reader or the student, the listener of this video, to take a look at this example 5 times, 10 times, 100 times if required, and understand each and every line of this program, because the program might be 6 lines, but it is 10 to the power 6 times difficult. It's difficult basically because you are looking at an assembly program for the first time. And an assembly program which is fairly complicated for the first time. So let me look at the 3 steps that we had in this exercise. The first step is we realize that the problem is difficult. So we wrote a small program in C. That's the first thing that we did. In the program in C, we had a product variable and an index that goes down from the number till 1. And at each point we multiplied. So we are doing exactly the same in assembly, nothing different. So the first is that we do a register assignment. So num is assigned to R0, prod to R1, IDX to R2. We start the iteration the same way as it's in the for loop with IDX equal to num in pretty much this statement over here. So then we do the multiplicative step, we multiply. And as I said, I'm making some simplistic assumptions over here that num is actually large enough. So I'm not doing some checks. So then the next step is once you do the multiply, let's reduce the index by 1. So let's have IDX equals IDX minus 1 with a subtract instruction and then we compare. So if you have reached the exit condition, which is if R2 is equal to 1, then we can exit the loop. So we don't have to do anything. The BGT instruction over here will evaluate to false. So we'll just simply fall down and evaluate the next instruction. Otherwise, if the index is still not equal to 1, we need to do another iteration of the loop. So we will jump to dot loop. So similarly, the loop will continue for num minus 1 times till the factorial computation is over. So I would request once again the reader to take a look at this several times, maybe work it out with a paper and pencil. And only when the reader is convinced, we actually move to slide number 54. So here is a food for thought burger question. Write a SimpleRISC assembly program to actually find the Ramanujan numbers. This is difficult, but can be done. It's a fair amount of work, but with the emulators that are there on the website can be done. So the Ramanujan number is a very interesting number, and so basically the story goes like this, that once Srinivas Ramanujan was very sick and his guide, Professor Harvey, had come to meet him. So the number 1729 was written on his taxi. So he asked Ramanujan, do you know what is the significance of this number? Right? Can you find something special with this number? Ramanujan, brilliant as he was, said yes. So 1729 is actually the smallest number that is the sum of two cubes in two different ways. It is 10 cube plus 9 cube. It is also 12 cube plus 1 cube. So it is a sum of two cubes in two different ways. So the question is, can you write an assembly program to actually compute the Ramanujan number? Well, the answer is very simple. First, write the program in C. After writing the program in C, gradually convert it to assembly. So the approach would be that we take all the numbers starting from, let's say, 2 till infinity, right? And we stop at the Ramanujan number. For 2, you essentially find out, is it possible to write it as the sum of cubes? Well, yes, 1 cube plus 1 cube. But any other combination of cubes? No. So you go to the next, go to the next. Keep going, going, going. You'll have multiple for loops. But the trick is first write in C, then do a register assignment, and then write it in assembly. That's the trick. If you are able to do this, our objectives are satisfied. Now let's discuss our last important concept in this subsection of the lecture called modifiers. So if you would recall, we had discussed that SimpleRISC supports 16-bit immediates. So it does not support larger immediates. So the question is that let's say I have an instruction of the form move R0 and -3. So what is it that would happen? So if we consider, so what is -3 in a 4-bit system? -3 in a 4-bit system is +13 or 1101. What is -3 in a 16-bit system? Nothing, just perform sign extension. It remains the same. So now the question is that when this is being moved to R0, which is actually a 32-bit register, what should be the default behavior if I do this? What should be the default behavior is that we have the contents of the immediate moved to the lower 16 bits, and the upper 16 bits is just a simple sign extension. So it preserves the sign of the immediate. So this is the default behavior which all of us expect should be happening, that a sign extension will happen. So essentially we are treating the 16-bit immediate as a signed number, and there is automatic sign extension happening. So this ensures that if we have represented -3 in assembly, -3 is also what gets stored in the register R0. But of course, since R0 is 32 bits, relevant sign extension is being done. Now let us define two variants of this same instruction, and these variants hold for other instructions as well, but let's only discuss this instruction. So let us define the move U instruction. So in the move U instruction, we treat the 16-bit immediate as an unsigned number. So essentially what happens is that in the 32-bit field, the first 16 bits is where the immediate comes in, and the remaining 16 bits are all zeros. So we treat it as an unsigned number. And in move H, what is done? So actually I have one diagram over here, but let me nevertheless explain it over here. So in move H, what is typically done is that again if we consider a 32-bit register with two 16-bit parts, so what happens is that the immediate actually gets loaded to the upper 16 bits, the most significant 16 bits, and the lower 16 bits are set to all zeros. So you can think of left shifting the immediate and then loading it to the upper 16, where the lower 16 are all zeros. So the U and H are generic modifiers. So the default is always to treat the immediate as a signed number, but we can use the U and H modifiers. So the U treats it as an unsigned number, and the H actually left shifts the immediate by 16 positions. So what is the mechanism? The mechanism is that when an immediate is specified in an assembly instruction, the processor will take the immediate and put it in an internal register which is not visible and convert it into a 32-bit number, right? So essentially the immediate is part of the assembly instruction, it's somewhere inside. This immediate is taken by the CPU and it is converted to a 32-bit immediate, right? And this 32-bit immediate is used in the computations. So for all arithmetic logical computations, this 32-bit immediate would be used. So we can control the generation of this 32-bit number internally. So the default is sign extension, but we can treat the 16-bit number as unsigned with a U suffix or load it in the upper 2 bytes, right? The most significant 2 bytes with the H suffix. So let's take a look at some examples. So let's first take a look at the default behavior of AB12 where the MSB is equal to 1. So in this case, we load AB12 in the lower 2 bytes and the upper 2 bytes consist of the sign bit, right? So this is, the sign bit here is 1, so all these 16 bits are 1. If we consider an unsigned, so then again the byte AB is loaded into this byte, and so AB and 1, 2 are loaded into lower 2 bytes. But the upper 2 bytes are set to zeros, right? 8 zeros and 8 zeros, 16 zeros. If we consider the same thing, move H R1 0x AB12, so AB12 are actually moved to the 2 MSB byte positions, upper byte positions, and the lower positions are set to 0. So let's take a look at some examples. So the main advantage of having modifiers, right? Why have them? The main advantage of having modifiers is that it is possible to load all kinds of constants into registers. Well, load meaning not from memory, but sort of store immediates in registers, all kinds of immediates in registers with a minimal number of instructions. For example, if you want to save FF, A3, 2B in R0, all that we do is that we actually move in A3, 2B into R0. So it will load A3, 2B in the lower positions, and upper positions will replicate the sign bit. Since the sign bit is 1, the upper 2 bytes will become FF and FF. If we want to set the upper 2 bytes as all zeros, right? In this case, all that we need to do is we need to have the U modifier, which will ensure that the most significant 2 bytes are zeros. Likewise, if we want A3 and 2B to be in the 2 upper positions, most significant positions, then what we do is that we will use the H modifier to move them to the most significant positions and set the rest of the bits or bytes as 0. So now let's look at a simple example. Let's assume that this complicated constant over here needs to be saved into R0. So this, if we didn't have the modifiers, it will actually take us a lot of instructions. It is complicated. So let us break down this problem into 2 simple problems and solve the problems in parts. So the first problem is that we need to take 1 to AB and load them in the 2 upper bytes. That's very easy. So we consider 0x1 to AB, right, in the hex form. We use the H modifier to actually move this the 2 upper bytes. Then we need to move A9 2D to the lower bytes. So this is also easy. So basically what do we have? What is the status of the register at this moment? Just before the second instruction we have 1, 2 and AB, and then we have 0, 0 and 0, 0 in the 2 lower bytes. So what we can do is that we can add this with 0, 0, A9 and 2D. So this will give us the final result, which is this result. So that's the reason we have an add instruction. We have R0 and we have A9 2D. But here is the catch. When A9 2D goes into the machine, it will be expanded into a 32-bit value. And in the 32-bit value, the lower 2 will be A9 2D, the lower 2 bytes. But the upper bytes will just replicate the sign of A, which is FFFF, which is not something we want to do. So that's the reason we specify the U modifier with the add instruction. So essentially the modifiers can be used with any arithmetic logical instructions and the move instruction, right? So let me say this again. The U and H modifiers can be used with any instruction that uses immediates, namely the arithmetic logical instructions and the move instruction. So in this case, in the second instruction, so this is instruction 1 and this is instruction 2. So in the second instruction, we use the U modifier to actually expand A9 2D internally into A9 2D, and the upper two bytes are 0, 0 and 0, 0, which is exactly what we want. Right? Had we not given the modifier, we would have gotten the wrong answer. To get the right answer, we add the u modifier to ensure that these two upper bytes are 0 and 0, and then we do the addition. So we get 1, 2, AB, A9 and 2D, which is exactly the answer that we wanted. So one thing that this example shows, so what is the take home point of this example? The take home point of this example is that to load a constant, I'm sorry, I use the word load, but the word should be taken in the context, in the connotation that you want to save an immediate into a register. So it would have otherwise been difficult had the modifiers not been there to actually put a constant into a register given our ISA. But with the modifiers, it has actually become easy. So we use the H and U modifiers, and with just two instructions, we are able to put in 32 bits into a register, which is great.